Second part of lecture 9, and here we start with talking about what are sandwich composites. Why do we want what are called sandwich composites? Because if you have only the composite by itself, okay, what is the density of a typical polymer matrix composite? Carbon is about 1.8 to 1.9 grams per cc. Most resin systems, most resin matrices are approximately of the order of 1 to 1.1 grams per cc. So if you have about 60% fiber and about 40% matrix, your density should be about 1.5 to 1.6 gram per cc. So even though this is pretty good, but you do not need to make the whole structure out of this composite material. First of all, it is expensive. Second of all, if you go beyond, say, 1/16 to 1/8 of an inch thick, 1/8 would be pretty thick. So if you go beyond that, it is going to be heavy. I mean, especially if your part is about 100 feet long, it is going to be pretty heavy. I mean, compared to aluminum, it is light, but still it is heavy. So you would like to reduce the weight as much as possible. So wherever possible, you would like to reduce the weight, and this is done by a methodology called you sandwich something. You sandwich an extremely lightweight material between two face sheets. Okay, so what are the components of sandwich composites? You have standard one, you have face sheets which are the actual composite material itself. You have a skin material that is an adhesive type of a material, and then you have a core material which is extremely lightweight. Extremely lightweight. So it can be of the order of, say, 0.25 grams per cc, zero point 0.5 grams per cc, and so on. Okay, so face sheets are traditional composite materials, and core materials can be, they are called honeycomb, and the standard manufacturers are Hexel or Plascore. And how they make it is like, for example, if it is made out of aluminum, it is extremely lightweight. It is like a piano spring, piano um, core. So when it is not expanded, it is a small block of material, but when you want to expand it, you just spring it out, and it is extremely lightweight type of material. So it determines the difference in um, the performance of the materials, performance of those materials. And those materials can be either aluminum, it can be aramid fiber reinforced phenolic. So again, they are called Nomex or Corex or whatever. Then, or it could be glass reinforced phenolic type of a material. So again, lightweight material or glass reinforced polyimide, a nylon, or a thermoplastic type of a material. And there are some other advantages to having these core materials. Say, for example, if you want uh, these materials to be fire resistant, your core material can be the extremely good fire resistant material that will prevent the fire from moving forward from the face sheet into the inside of your component. You can also have foam type of materials, which could be either closed cell rigid foam, it's called Rohacell or Divinycell or polyurethane. So Divinycell is very lightweight uh, polymeric foam, polyurethane foam, and um, the other advantages of these foam type of materials is that it has got fantastic acoustic protection against sound and noise and things like that. So again, I mean, if your aircraft needs to prevent the outside noise to be coming inside, you need your composite material plus the sandwich material to have extremely good acoustic properties. Or you can go one step crazier. It's called balsa. It is one of the lightest density wood type of materials. So balsa wood. So it's extremely lightweight. And for example, some of the UAVs and all are made out of, I mean, sometimes the whole wing structure is made out of balsa wood. You just put a very thin sheet of composite material to give it the strength required, but still the lightweight is obtained by having the core material made out of balsa. So how do you make this structure? You have to adhesively bond these structures to the face sheets. And if you are doing a wet layup, then you would use the resin, you would use the properties of the resin used in the face sheet to do the bonding. But you can also use an adhesive that will melt at around the same temperature as at the composite fabrication. So the magic temperature is 350 degrees F or 175 degrees centigrade. So there are several, or if you are going to use a face sheet that is going to be cured at 250 F, you use an adhesive that melts at 250 F, or if you are doing the curing at 350, you use the adhesive that melts at around 350 degrees centigrade. It is a film adhesive, and you just place that and you just press the face sheets, which is separately made, and then you just cure it together. So what are the ways in which you make these materials? You have to form it, you have to machine the sandwich materials, you have to machine the face sheets, etc. And for the foams itself, you could be making it by a foaming process. So you take the polymeric foam and you gasify it to create the foam type of material. And then once it is done, I mean, you have to clean it and you have to vacuum that. And if it is aluminum based material, then you cannot have any kind of adhesive, anything sticking to it, and it should be completely clean. Otherwise your composite material is going to have issues with as far as the properties are concerned. So you have to do vapor degassing, degreasing, or and you have to degas the material so that there is no gas produced during the processing of the composite material itself. And Nomex is a paper core, and you can use ethyl alcohol, which can evaporate, and you apply that to get the right kind of cleaning. And if you don't have it cleaned properly, then it is not going to bond to the composite material. Then you have to dry it, and you can have the face sheets that are co-cured or post-bonded. And one thing you have to make sure is that you are not crushing the core material, because the core materials are going to be extremely lightweight and fragile. So you want to make sure that they are bonded properly to the face sheets. And there should not be any kind of intercell buckling that takes place during the curing process. And additional considerations are that suppose you have to fasten something or you have to bolt something, you have to ensure that the bolting point or the hard point for the fasteners do not damage the sandwich structure. And the way you do it is by you have to attach the fasteners prior to the processing itself, so that you are not creating any kind of weak points into the material after the part is cured. Next, we want to talk a little bit about composite joining. So, why do we not want any kind of bolting? You do not want any bolting because you do not want multi-materials, which can be a cause for fatigue as well as corrosion. Okay, so most of the time composite joining is done by adhesive bonding. So, and why is it important? Because you make the making the material is not sufficient. Say for example, if you have the wing structure, the wing is made separately. You bring it back into the assembly shop, and then you have to join it. How do you join it? Do you create holes and put bolts through that? Maybe in the old days you would rivet through the whole structure in the wing, but you don't do that anymore. Okay, uh, and creating fasteners and assembling them together is sometimes extremely expensive, and it also creates a weak point. Okay, so in big structures especially, the Achilles heels of those structures are the joints, and in this case you cannot just go to a handbook and look it up to get the right tools, right machine and processing procedures for joining those composites together. Okay, so this one I took it from a guy from who defended his thesis at University of Dayton. So I thought these were uh, some really interesting and important points that he was making as far as joining is concerned. Okay, so what are some of the objectives of composite joints? First and foremost is that it should have good mechanical properties at even at extreme conditions, and especially if it is a commercial composite structure and you are trying to make sure that it has got good lightning strike mitigation and EMI shielding type of properties, then it should provide a conducting path to the whole structure. So you would also like to have these bonds to be electrically conductive. This point, it may be important, but it may not always be important. But you should definitely try to reduce the weight of the composite material. And most importantly, it should be easy to repair. And once you make it, it should be easy to inspect through NDE and apply quality controlling processes for this composite material. So the first technique is obviously the adhesive bonding. You do have some places where you might do mechanical joining, and or you can have a combined adhesive and mechanical joining, or sometimes you might also do co-curing. So you put the film and you co-cure the composite material so that the whole thing gets infused with the adhesive bond as well as the resin matrix itself. And the next one, it was used a lot, but not as much as it used to be before, which would be stitching. So you stitch through the thickness, and it is extremely tough to do that. if you really need it, you can do it, but not always. Mechanical bonding, there are some advantages like, it is very easy to repair and easy to inspect for quality control. They are simple in construction, so production is faster, and it is not typically affected by environment and temperature, except that if it is multi-materials, it can undergo corrosion, so which is not always a good thing. And you do not always need a neat room, a clean room and environment. So it's not neat room, it is clean room. Environment like the adhesive joints. And you can get good joint by adding extra composite material, uh, metallic reinforcements, etc. But the problem is that it will introduce extra weight into your composite material. So mechanical joints do have some disadvantages. So if you want mechanical joints, you have to drill the composite. So what is the problem with the composite material? Composite materials are extremely harsh, and um, if something is very abrasive because of the composite, because of the carbon fiber, is very abrasive, or even glass is very abrasive. So you and the other thing is that the fibers will dissipate heat in a certain manner, and the matrix will dissipate heat in a different manner. So if you are drilling a hole through your composite material itself, the matrix will melt while the fiber is going to chip off or break off rather than getting drilled through. So what happens is that if you have a very thick cross section, it becomes extremely tough to push through the whole composite material, and in this case you would end up with localized areas of melting, and you may even have unacceptable delimitation or delamination on the exit side. So you have to, first of all, you have to have diamond coated tips, or titanium nitride coated tips, um, and you have to have an optimum speed of drilling so that it will give you good quality, and you don't want the fibers to break and create weak joints here. You don't want to do that. You may use a different kind of a weave on the top and bottom surfaces so that it becomes easy for you to drill right through the whole composite stack. So it's always something to be noted. Okay. So what are the common types of bolts and screws? Titanium, aluminum, or cadmium coated stainless steel. And but the problem is that bolts and nuts may exceed too much compressive forces, and the materials can be deformed. If your composite material has not been designed to be very strong in shear, then these screws may not hold that large weights. And the larger the structure it is, your bolts and nuts are going to be the stress concentration points. So not a good thing. Okay. And fatigue, solvents, water penetration, etc. are bad news for these mechanical bonds. And the other thing is that if you have composite joints with bolts, the hole has very poor performance in tension. In fact, you will see that there are a lot of papers that talk about having a composite structure in tension. I mean, so it is, those holes have poor performance in tension by almost 20 to 50%. So you have to take all that into account. And these are made from metals, so which means it increases the weight. But sometimes people are trying to use nuts and bolts that are made out of composite itself, but it is not very easy to make them. It is not very easy to machine them. So it's not very easy for you to join composite structures using mechanical bonds. And if you have aluminum, aluminum can cause galvanic corrosion with carbon fiber. And it is not a good thing. And if there are gaps present between the fastener and the composite, you have to use what is called a shim. I don't know if you know what is a shim. A shim is a very thin sheet of material, and you would use that, you would slip it between two panels which are going to be joined. And in that process, again, these are going to be different materials from the actual composite itself. So it can actually be bad news as far as the galvanic corrosion is concerned. So this would be a standard process by which it is done. So if it is going to fail, what happens? It will fail at this point. If it were not there, it would not fail there. Sometimes, it might even fail here. So part of it will get chipped off. So you have to go and repair the whole structure or throw away this structure and start with a brand new structure. So it's not a good thing from a manufacturing point of view. So the most common one nowadays, they are trying to move over to adhesive bonding. And there is a wide variety of materials available when adhesives are used to bond materials together. And it creates, especially with composites, some of these adhesives are being used because of issues with mechanical bonding. So this is a standard method, and it is a more accepted method of joining, especially if you have a large structure. Having an adhesive bonding is probably better. And the most common polymers in the structural adhesives classes are epoxies, polyurethanes, acrylics, cyanoacrylates, silicones, and phenolics. What is cyanoacrylate? What is the trade name for cyanoacrylate? Have you heard the name araldite? So that is araldite. Okay, so it's a standard material. It has got very good strength, and it does not get affected by the UV and moisture and etc. So how do you select a proper adhesive? You have to look at the thermal conductivity of the adhesive, so that if you have a structure that is being exposed to elevated temperatures, you want to remove the heat. So that adhesive also has to be able to conduct the heat through the joint. It has to be chemically compatible with the resin system used in the composite. It should have proper viscosity so that it doesn't run off, or if it is too viscous, then you have to make sure that it is applied evenly throughout the composite material. Then obviously temperature resistance and mechanical strength of the adhesive are also important parameters. So this tells you something about the process by which addition works. So that those are the fundamentals. I will not bore you with that. But before you bond a joint together, you have to treat the surface. You can either do plasma treatment, or you can do surface cleaning in the presence of heat. I don't know how many of you heard about a place called Tucson, Arizona. That's where I came from. That's where I used to work before. And it is the one of the largest Air Force training centers for pilots. So every couple of seconds, a fighter jet is taking off and or landing. And what they had to do was they had to clean the joints or clean the aircraft, and they would use a solvent called not chloroform but trichloroethane or CC, I believe CCl4, CHCl3. That's what I remember. So the problem is that CHCl3 goes through the, I mean, so if it is washed out, it goes through the ground into the groundwater system. So nowadays, many of these solvents are not being used at all, or they have tried to go to solvents that are much more environmentally friendly. So you have to treat the surface, you have to clean the surface, then you finally clean it with heated distilled water, and then you apply the bond, and then you have to remove the extra adhesive on the surface by abrasion or by shaving the surface, etc. So you cannot have anything extra at all, and it is a good thing. Okay, so it's a clean process. So you need to have good viscosity, make sure that it has got good wetting. So good wetting means the values of the uh, of the of the bond is like, so you have to make sure that the adhesive is spreading very nicely across the surface. It cannot ball up. If it balls up, it won't be a good adhesive at all. So viscosity is an extremely important point, and it plays a very large role in the selection and designing the adhesive. And then you cannot just apply the adhesive liberally. You have to make sure that you use just enough so that it bonds well. Okay, so you don't make the adhesive bond like 5 millimeters thick. It could be maybe a couple of millimeters, couple of microns thick. For those of you in this class like Josh or Tyler might be able to recommend more things to learn and read about adhesive bonding. And the other thing is that you have to make sure that the bond length is right. Okay, so if you have an entire surface to be bonded, like if this whole surface has to be bonded, you don't put like 1 2 3 4 every couple of points. So you probably apply it through the entire joint, so that when you test it, it is going to withstand the um, temperature, pressure, and stresses, etc. So what is the effect of surface roughness? Surface roughness means if you roughen the surface, you will get good adhesion. You get high surface area that is available for the bonding, and but the disadvantage is that on a rough surface, you cannot get uniform wetting, as the resin cannot penetrate into small pores, and you may find some air gaps at the interface of the adhesive bond in the case of a rough surface. So what all ways in which can the adhesive joint fail? You can have what is called a cohesive fracture. Um, you can have interfacial fracture, so it fails, the joint itself comes off. You can have mixed failure, and you can have failure of the adherent or the adhesive itself. I'm sorry, there is a lot of write up here, so please go through that. So essentially the takeaway is that um, there are not too many NDE techniques for looking at adhesive joints, but still there is some QC, and repairing of complex adhesive joints is a big problem. So instead of all this, why can't we have a combination of mechanical and adhesive joining? You can, but it's not always preferred. Um, and you can have fast curing adhesives as a method of rapid assembly before the permanent mechanical joints are installed. So you drill a hole, then you bond the two joints together, and then you apply the nut and bolt to bolt it together. So you can do that, but again, it makes it a very complicated process. So the other joining method is called stitching. So you can do stitching of the composite layers, but in this case you may not do complete curing of the face sheets. So you do the joining before the face sheets are cured. So what kinds of stitches are used? I mean, you can have a lock stitch, modified lock stitch, or stained stitch. So these are all different ways in which you can join them together. So here is a schematic of the joint types, and this is what is used for a lot of stitched joints. But nowadays people are moving away from all that and sticking with the um, type of joints that are used with addition. So what are some of the defects that you can introduce into the composite due to the stitching? So you can create, so suppose you drill a hole, you are breaking the fibers in certain directions and orientations, and that may not always be advantageous to you. So you can see the mechanical properties. So if you take glass polyester type of composites and you stitch the composite material with between two layers, you can see that joint, the strength of the joint goes down drastically. So you don't want that to be the case. You would like the composite material to be as good as possible. So again, this shows the mechanical properties of some of the uh, stitched composites. So you can see that if you have cotton stitches, the strength is slightly lower than no stitches. If you have carbon stitches, it is even lower than that. So again, this shows the mechanical properties of stitched composites. It's an easy process, so that's why people still follow that. So the other method, the final method, is co-curing. So this is very good for joining small composite parts. And but when you increase the size of your component, this is not very useful method, because the size of the autoclave is limited, and there is very little chance for the repairing of the composite if there is anything that is going to happen uh, during the curing process. So if you want to repair something, this is not a good method. So these are some of the references for repair and joining. So please go in and take a look at some of them. It may be of some interest to you, especially if you are writing a paper on composite repair. So anyway, or composite joining. So if you want to do that, you can use these papers. Okay. So that's all I have for this class, and I will stop right here.